we completely messed up in terms of assigning dark to dark energy and to dark matter. Like, it was a fraud in terms of marketing and definitely not the best decision.
Hello, everyone. This is the Space Cafe podcast, and I'm Marcus. Let me read something to you. I'm a theoretical cosmologist working to understand how the universe began, how it evolved, and what its ultimate fate could be. I'm like, how cool can it get to really go down into the weeds, into the nitty-gritty of everything, of the big questions. I immediately knew I had to sit down with the author of this line, and especially when I found out that she's also part of the Euclid consortium. You know, the Euclid spacecraft that launched 1.5 years ago? And that was designed and targeted to probing our universe, a considerable swath of our universe, for traces of dark matter. The greatest, or one of the greatest mysteries of them all. And the person I'm sitting down with today is part of the inner circle of that spacecraft. I'm humbled to sit down with you. Thank you for taking the time. Guadalupe Cañas Herrera, thank you for being on the show. Let's go. If Euclid delivered the most optimistic results you could ever wish for, what would it be?
Well, Euclid is already delivering the most exquisite data that I have ever seen. The raw data is amazing. So my imagination is free to fly and go wild. I would expect that we are able to reduce our statistical uncertainty so much in our measurements that we can definitely rule out what we call the standard cosmological model, which is the model that we have these days to explain most of the observations that we see in the universe, but pretty much tell us that 95% of the universe is composed by dark energy, on 70% responsible of the acceleration of the expansion of the universe, and dark matter on 25%. So I'm really looking forward that the statistical uncertainty associated to Euclid measurements is so small that when I'm comparing alternative cosmological models that tell us something about the nature of dark energy and dark matter can potentially be statistically consolidated instead of this concordance model. That would be my dream. And that is definitely what we are really looking forward to and working hard in the next decade to come.
Do you have a hunch? Do you have a gut feeling? And I know this could be very tricky because especially in the scientific community, there is no gut feeling. There is the mind, but maybe there's a little bit of a feeling one could have in what direction things could go.
Yeah, I actually do believe that scientists must follow their own instincts sometimes. It is true that most of these, what we would call instinct, is developed by our scientific expertise and our scientific experience. I do believe that we're more close to understand this accelerated expansion of the universe by revisiting the theory of general relativity of Albert Einstein, instead of just assuming that there is an unknown substance that we don't know anything about that we call dark energy. I prefer to believe that mathematically we are still not there yet, so we must revisit the equations that explain the laws of gravity, instead of thinking, okay, we have some kind of hidden fuel that it is driving this accelerated expansion. So I'm more inclined towards believing that modified gravity theories, this is how we call them, so theories that revisit the equations of Albert Einstein, will have more, a more protagonism and something else to say with respect to, just purely dark energy theories. That's my feeling. Let's see. Yeah, let's talk about this within 1 decade from now.
Dark energy, dark matter sounds a little uncomfortable. It sounds a little darkish. So maybe it's not the optimal terminology to use, because dark just means we do not know.
Yeah.
I think this is the most important thing to take away. There's nothing dark out there. It's just something we do not understand.
actually, I always say, and you guys need to be with me and bear with me until the end. We are physicists. We are theoretical physicists, especially the people who are performing like more theoretical cosmology. We come from a more theoretical side from physics. Astronomers tend to be extraordinarily more catchy, but we completely messed up in terms of assigning dark to dark energy and to dark matter. Like it was a fraud in terms of marketing and definitely not the best decision. It is true that, okay, so the first discovery was dark matter, and the term dark, in that case, it is indeed referred to the fact that we believe that it is a type of matter that we see that interacts through gravity, but it doesn't interact with light. So we cannot see it. And this is how the term dark was associated. It makes sense. When we definitely messed up was with dark energy, because in that case, dark really refers to the fact that we don't know anything about it. That is there, that we cannot see it, but we don't even can predict if it interacts with light or with gravity. So definitely it was, one of the worst terms, one of the worst marketing strategies that we've done in cosmology so far. I always say that, okay, dark matter, it does not interact with light. We cannot see it. That is the fair game. So it is dark. Dark energy was just a way of, parametricizing our ignorance. Yes. Yeah.
Let's just try to unpack this topic of the importance of finding out what this is that we do not know. So we're sitting 1.5 meters apart from one another right now. Is this dark thing, this unknown, between you and me?
Yes.
Or is this at different scales?
So for dark energy, you mean? Yeah. So dark energy, in the case that, so we believe that there is an unknown substance, that it is all over the space-time. In principle, yes, we must have that substance that we, in theoretical physics, we just parameterize. So when we write the equations, we use the most simplistic way of understanding or using mathematically how to define that substance. But yes, so we believe that it is all over the space-time. However, if its effects are more plausible, so they are larger seen at very long distances, so a very large scale. So even though it's everywhere, its effect maximizes the longer the distances are. This is why it was really tricky to actually discover dark energy, or in fact discover the accelerated expansion of the universe, because you really needed to reduce, as I was saying before, the uncertainty of your measurements to be sure that when you were measuring this rate of expansion of the universe, you could see some hints of acceleration. And for that, you really needed to go to very long distances to study like objects that are really, really, really far away from us. And only when we have the technology and the capacity to measure those objects, that in this case were in a specific type of supernovae, is when we had the capacity of figuring out, our universe is expanding in an accelerated way. So definitely dark energy, in principle, everywhere, but we get to see its effects at very long distances.
What kind of effects are you observing?
So actually, dark energy is behaving pretty much in contrary to gravity. So gravity tends to cluster, to make together different objects in the universe. The larger the mass, or the more heavy they are, the more they are going to tend to cluster. So this is how we have, stars forming galaxies, then galaxies joining other galaxies to form clusters. Then in the case of dark energy, is precisely the opposite. So what we are seeing is that the space between objects, objects in the universe that are heavy, that have mass, is driving them apart. Mm-hmm. So it's somehow, so...
It's like between magnetic poles, like equal magnetic poles?
Yes, exactly. So in some sense, like it could be a nice analogy. So indeed, so they're like different forces physically speaking, but we have like gravity pulls things together, mm-hmm. and then dark energy pulls them apart. So actually, this is why it was so puzzling when we discovered the accelerated expansion of our universe, because if you take the equations of the theory of general relativity, and this is an exercise that I really love to include in the set of seminars of my classes for general relativity with my students, it's like, okay, I'm telling you the universe is composed by, 30% of matter and few traces of other things. Calculate what will be the expansion of our universe. And what you get to see is that our universe is expanding, but is slowing down in its expansion. And this is what we believe that potentially could happen. So when we discovered the accelerated expansion of the universe, we're like, what? Exactly, because suddenly you need to come up with something that will drive that acceleration, because like with the different components that we were already observing, there was no way to explain that.
How do your students react when they observe something like this?
I love to teach general relativity because is the course, especially the general relativity ones that we touch the latest part of the course, which is when we apply this to cosmology. Because first of all, like people think of the theory of general relativity of Albert Einstein to be a very complicated and difficult course to follow. And it is true, like mathematically, it requires like some techniques that are advanced. But when you apply the equations to cosmology, you simplify many things. Like we really model our universe to be very simplistic at the end. So the fact that the students are able to really come up with results that are not that old. I mean, we discovered the accelerated expansion of the universe at the end of the last century. So the end of the 19th decade, that they are able to reproduce those results is always like, wow, this was a Nobel Prize. And now I'm able to actually reproduce what they did and understand the impact. So it's interesting to see how many of the people that decide to pursue a career in cosmology really have fallen in love with cosmology at the limit where they are studying the theory of general relativity. Yeah.
How much do we know today as opposed to 100 years ago when general relativity was uncovered?
Yeah, this is a very interesting question because the theory of general relativity opened up what we called really the field of cosmology. So it is when it basically theories trying to explain the very first early moments of our universe, the theory of the Big Bang, how the first nuclei of atoms were formed. All that knowledge was developed thanks to the flourishing of, particle physics, high energy physics that took place more or less at the same time as the theory of general relativity of Albert Einstein. And I feel that we had a boom of most of the content that these days is still taught in masters of cosmology all over Europe is pretty much, I would say, 70% of the content of those courses is still based on those theories. But it was exactly the discovery of the accelerated expansion of the universe, what it brought, what we call colloquially modern cosmology. So really revisiting everything that we thought that we knew and give it a twist to be able to think forward. And in that sense, that is really recent. So we've been doing that on the last 30 years. So that is also why it's so challenging to study dark energy and the accelerated expansion of our universe. Because in 100 years, we had the time to really test really well general relativity. Our GPS are working. We have spacecrafts that we have sent all around the solar system. We still could communicate with some of them until quite recently. We have tested the limits of what we call the theory of general relativity with our solar system. And they're already pretty large distances. So if you really want to break the theory and bring back like some modified gravity theories to explain this accelerated expansion, they still need to pass what we call our solar system tests. So whatever theory you're proposing, at least it has to work really well as the theory of general relativity, the standard one in the solar system, because we have measurements out of it. And this is a challenge. Like we're really opening up a book in the history of physics where modern cosmology will take more and more protagonism, and it will be happening together with technological development, such as Euclid in this case.
Like Euclid, are we still in the phase of poking holes into a great big unknown? Because I'm just wondering how far we are toward understanding something. Because I guess Euclid is now sort of trying to find out what this three-dimensional space-time looks like, to then in order to find out what the distributions of objects and dark matter could look like. But this is just a beginning to map the territory, so to say.
I would like to be a little bit more optimistic.
Yes.
Definitely, I do have very hard days as my job as a scientist and as cosmologist, that I wake up every morning or like a morning, maybe once every month. Like I have these feelings of, oh my God, I'm dedicating my life to something that is extraordinarily fascinating, that it is really plausible that I will finish my career not being able to understand a 0.0 whatever % of what the universe have to offer. And while I might think, even though I might feel discouraged, that discouragement lasts only 1 second, I have to say. Because later it was like, there are so many possibilities that I think is so good in some sense. With respect to what we are today in modern cosmology, once that this accelerated expansion of the universe was discovered and was measured experimentally, we had very important cosmological missions that have studied the universe. And there is a lot of work that has already taken place, understanding how our universe was behaving when it was a child, when it was an infant. That is with the observations of what we call the cosmic microwave background. So the first light, the first photons, those first light particles that managed to start traveling through the universe, once that our universe cooled down sufficiently, only 300,000 years after the Big Bang. And there has been a lot of work in understanding or studying that relic radiation. And we built the knowledge that we have these days about our concordance, our standard cosmological model based on those measurements. So I wouldn't say that with Euclid, we are going for the very first time on something. We are really building up. Yeah. So in the history of our universe, we have understood, or we have developed lots of knowledge, really important knowledge about the early universe. Now is when we are moving forward and we are studying how the universe looked like on the last 10 billion years, which would still correspond to a very substantial fraction of the life of the universe, but we are moving to what we call late physics. So we are going to study the universe how it looks from now until the past, but we are not looking that much on the past as with the cosmic microwave background. So in this sense, I do feel that definitely there are many things to understand, and it is the first time that we are envisioning something as ambitious as with Euclid, but we are building up. So at the end, the question is not, let's see how our universe works. The question is, okay, the model that we have, that it was really well supported by the observations of the cosmic microwave background, does it still hold? And I think it's really important to put in perspective the question that we are aiming to tackle. So definitely tons of work to do, definitely tons of forward thinking in terms of what it potentially could be next. But this is not just the beginning. I would say that this is a consolidation of modern cosmology.
Fantastic. Let's talk about Euclid.
All right.
So Euclid has been around now for how long was it now?
Like 1 year. So yeah, 1 year and like few months. So we launched Euclid on the 1st of July of 2023. I had to be like really careful all these days because I wasn't like Euclid launched last year. No, it already launched like almost 2 years. Yeah, exactly. Almost 2 years ago. Time is flying. So Euclid, when it launched, it worked over few months on its performance verification and commissioning. So basically,
Where is it positioned? Where is it sitting? Where is it observing?
Euclid is in the most posh, popular, and expensive neighborhood of our solar system, and that is the Lagrange Point 2. So it is a really interesting quasi-static. I don't like to call it point because people think that really will be the size of this room where we are here. It is an area of a space of like thousands of kilometers where you can put a lot of missions to work together, and they will definitely have space enough. But yeah, so it is a special point between the Earth, the Sun, and the Moon, in which Euclid and other missions such as James Webb or Gaia, that actually we are saying goodbye really, really soon to Gaia. And this is one of the reasons you need to make space for new missions to come. But what it is really interesting about this particular point is that the Sun is always behind the spacecraft. So we have constant flux of electric energy through our sun panels, but we get to see to the deep universe, which is what we are really aiming for, because we would like to take pictures of galaxies that are millions of years from us. So yeah, so this is where Euclid has been operating. So it launched on the 1st of July of 2023. We had like a fantastic, really smooth launch. We reached our destination quite, easily. And then we started working, as I was saying, performance verification and commissioning. That translated means, okay, you switch on your instruments and you start calibrating your instruments and verifying that everything is working according to what you thought that it should be working. During the performance verification, we did have some challenges to overcome. We did, which really put as a manifest the fantastic work of so many people of our teams behind. And then on the 14th of February last year, I always remember, was St. Valentine's, we started the Euclid-wide survey. And what is the Euclid-wide survey? So it is basically this 3D map. So we're taking pictures of 1/3 of the sky. We classify what from those objects that we see in the pictures are galaxies. For at least 1.5 billions of galaxies, we are measuring the 2D position, their shape, and their distance. And through this distance is how we access these time dimensions, because distances in the universe have some time component, as nothing can go faster than the speed of light. The farther away those galaxies are, the older we are seeing that galaxy to be.
How do you measure a distance between an object, like two objects that be behind one another?
Oh, yeah.
Very far away. How do you do that?
Yeah, so Euclid has, this is a reason why Euclid has two instruments on board. So one is a camera, like pretty much similar to the cameras that we have in our phones. The other is our near-infrared spectrometer photometer. So it is an instrument that basically operates, as the name says, in the near infrared. There is a reason why we are tackling the near infrared, and it is the fact that we know that galaxies that are suffering right now this accelerated expansion of our universe, their light that reaches us, most likely it is in the near infrared size of the spectrum. So this is why our instruments are tackling the near infrared. And how do we measure the distances? Well, we use the concept of redshift, which is really similar to the same concept. Well, it's actually, I would say, not really similar. It's literally the same as when you're driving your car and suddenly you get to hear an ambulance or like a police car, exactly, the Doppler effect, yeah. So you get to hear, if it is approaching you or it has already overcome you based on the sound of that siren. We can extrapolate exactly the same concept to light. So our NISP instrument measure that redshift based on two different techniques. One is photometry. The good thing with photometry is just it measured the redshift associated to photons that we are collecting in our cameras. So good thing, you can collect tons of photons. But unfortunately, this technique is less precise. So we try to compensate the fact that it is less precise by measuring many, many galaxies. With a spectroscopy, what you do is that you decompose that light that it is coming from those galaxies, and you really compare one per one of the different elements that those galaxies have if it is hydrogen, helium, oxygen, with light spectra that you have on Earth. And seeing how much these lines have been reshifted or they've moved, you can infer a distance from galaxies. Now, coming back to your question, spectroscopy is really good to be using for objects that they are overlapping each other, because especially if those galaxies have different composition, you could distinguish like which spectra will correspond to each galaxy, and you can make many, many measurements of distances of galaxies. And this is one of the joys of the instrument of Euclid. For the very first time, we are aiming to do a spectroscopy from space for many, 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 many galaxies. So it was not a challenge only on the technology, it was a challenge from the data processing side. We are working on this. I'm really looking forward to you guys to see the first results of the spectra, although actually you could see already some spectra from the early release observations of Euclid, what we published on our results. But yeah, so basically we use redshift to measure distances to galaxies.
Where would people go to check out those results?
So within the European Space Agency, we've done an extraordinary work to bring our Euclid information up to date, just to keep you posted of everything that it is happening with our spacecraft. So if you just simply type like esa.int/Euclid, you will be able to find like all the information, and in particular, all the data associated to the early release observations, and already next week with our first quick data release. You will be able to access all these data. So not only the scientific results in publications, but really the raw and calibrated data. So if you're interested in a spectra, please be my guest.
So you're observing not a flat shape. You're not producing flat images like what James Webb does, what Hubble did. You're producing three-dimensional observations. So, for example, like a three-dimensional cube shaped, and whatever is inside that cube that is of interest to Euclid. So, how deep is the z-axis? So, how many, I don't know, parsec or light years do you go?
Okay, so two points to sit down in here. So the first one is that we do have, the first raw product are 2D images. So we always have like 2D images. The key of what Euclid is doing is what we called in the field tomography. So we take many pictures and then we basically layer exactly. So we stack all these images based on the classification to distances to galaxies. And this is how we reconstruct the Z axis. So how far are we going? 10 billion years, which is is a lot, like 10 billion light years, which is crazy. So it will correspond in those who are like more within the astronomy language. So we are targeting between redshift 0 and up to redshift close to 3. And we know that dark energy started dominating. So we started to see these effects of the accelerated expansion of the universe around redshift 1 point something. So really the Euclid map, so this Euclid 3D map was designed to basically map what it was happening before dark energy domination and during dark energy domination. So we could measure this accelerated expansion of the universe. So you do not send to a space billionary spacecraft without your scientific case really well studied and understood. So every single piece of technology that Euclid has on board has been designed with this specific purpose, that this map that we are measuring or that we are aiming to produce have to have like really strict statistical measurements and uncertainties so that we can say something about the nature of that energy.
A first batch of data got released already last year. That was already scientific, but it was a demo set of data, right?
Yeah. So the first release of data happened actually the end of 2023. So yeah, it's exactly. So again, it's crazy how time is flying. But yeah, so the first release of what we call the early release observations of Euclid were pretty much released at the end of 2023, and it contained few information. In this case, The data of Euclid was more focused on what we call legacy science. So what is legacy science for a cosmologist like me? Everything that you could do in terms of understanding the evolution of galaxies, the interstellar medium, clusters of galaxies, globular clusters, but not necessarily you can do cosmology with it. And what does differentiate between legacy science or legacy astronomy science, extremely important actually, like I'm falling more and more in love about that, or cosmology. Basically is the area of the observations and the area translate on the number of objects that you have. For Euclid, we are targeting on galaxies. So to do cosmology, you need billions of galaxies, millions of galaxies. So the early release observation program was extraordinarily powerful to show that our instruments are up for the challenge to be able to produce cosmological results in the future, or in terms of understanding overall how our universe works. The data set was really reduced. Now next week that we're going to have, so once that we release our first quick data release of Euclid, the area is going to be like around 50 square degrees. And 50 square degrees is a mini patch of what we are envisioning to have for the first cosmological data release of Euclid, that it will be around 2,000 square degrees.
So can you give me an analogy what to those square degrees? So for example, we all know, or some may have known, if you hold your thumb up at the night sky, I think that's 1 degree.
Yeah, something like that. So so just to give you a really small analogy, the first time that we envisioned to do this kind of maps from space using already available data, for instance, from the Hubble telescope, the area that it covered was as if you will put your finger, like your middle finger, it doesn't really matter, up to the sky, and then it will roughly correspond to the white patch of your nail. Okay. Now with Euclid, we are doing literally 1/3 of the sky. So so everything that you could potentially see that is not contaminated with the light of our own galaxy. In total, that 1/3 corresponds to roughly 15,000 square degrees. And as I said, the first time that we were doing like some of the first surveys, some of these first maps that were produced either from space or from telescopes that we have like in our Earth, in the ground Earth right now, was like 20 square degrees. Wow. The first time, like 10 years ago, so that I visited the US, that I was an exchange student, the first contact that I had with cosmology was one of the precursors, like one of these first galaxy surveys that they were being developed, that paved the way for later doing what we do with Euclid. And I was working with 20 square degrees of data. And now 20 square degrees of data is half of the first Euclid data release. It's amazing.
I was surprised to very recently hear that in 30 years of operation, the Hubble telescope observed 1% of the entire observable universe.
Yes.
This is crazy in 30 years.
Yeah, I know that people always ask me, why have we, I think it's a really valid question, and it's a question that it is worth thinking because it really rooted us again into the principles of Euclid. But like a really first question that I get from relatives, friends, or overall the public is, why have we spent so much money to put another telescope in space? So what is Euclid offering us that Hubble could not, James Webb cannot? And it is a really valid question because Hubble and the new James Webb Space Telescope, they are so powerful. They are offering us insights of the universe that they were completely hidden to us before. So why Euclid? The difference is the field of view. So as you were pointing out, like in 30 years of operation of Hubble, like we just managed to have images of the universe that were like 1%. 1%, we achieve it with Euclid in 2 weeks. So every time that Euclid takes a picture, the field of view is so large that this is what allows us to take pictures of 1/3 of the sky in 6 years operations. So,
but it's not optical, isn't it?
It's optical and near infrared, both of them.
But if you compare it to the image quality of Hubble, because that's very popular, How does it compare?
So in terms of Hubble, our sharpness in images, both in the visible and in the near instrument, is really similar. So the quality of images that you will have with Euclid in our visible instruments and Hubble are pretty much the same. So if I would put you actually a Hubble picture and a Euclid picture, and I will not specify, you will not be able to tell me which one is coming from each telescope unless you're seeing the diffraction pattern of stars. That will give you like some indications. Now, with respect to James Webb is fantastic. I always say like James Webb is amazing as a magnifier for the universe. So the instruments of James Webb are designed to zoom in detail. So this is how, if I put like an analogy with Euclid, you will be able to, in one snapshot, take beautiful images as the Perseus cluster, where you have like millions of galaxies just in one single view. With James Webb, you will be able to resolve the star, how stars are being born in some arms of those galaxies. Now, can you take like this field of view with James Webb? Definitely, but it will take you centuries, and we don't have centuries to be mapping the universe. One of the biggest challenges that we have from Euclid, from the technological point of view, is that there is so much data that how do you bring all of that information back to Earth? So this was one of the biggest challenges during the design phase of Euclid, because it required preparation, not only at the level of like telecommunications, but preparation in Earth. So we needed to build like different antennas to retrieve the information that Euclid is sending us in our K-band, which I find fascinating. And also Euclid is one of the first missions that have a hard disk on board. Really? Yeah, because it was...
Solid state?
Yeah, actually, I don't know. But I mean, every time that you're sending a spacecraft into space, one of the biggest handicaps is how much it can weight. So at the end of the day, like the more heavy a spacecraft is, the more you have to spend it to put it in orbit. So you always need to have like the sweet spot between these features. But with Euclid, we could not risk that we cannot retrieve 1 day of observations, because 1 day of observations is a lot of data, and it will significantly affect. It's a lot, just terabytes every night. So every day that we are basically connecting with Euclid, because with Euclid we are seeing. So we take like a snapshot of one part of the universe, and that we get it like in the visible and in the near infrared. So that is already very heavy data. Like imagine the best quality. This is something that an exercise that the public or everyone could actually do. Please do me a favor. Like my father is so addicted to this, and actually I love it too. But go to ESA Sky and look at the latest Euclid pictures that we have released and try to open them up in 50K times 50K quality. There is a reason why we don't give the public the option to download those pictures.
15 times 15.
15K. 15, so 1515. Yeah. So, I mean, the amazing quality that you have, like you could spend hours and hours zooming in and finding things. Yes. There is a reason why we don't give the public the opportunity to download them, because they are extraordinarily heavy and it will be basically giving us some problems with our servers. But even if you try to download like on a smaller quality, you will already see how heavy they are. And those images are processed. They are not already the raw data. So they have like some filtering. So that will already give you an indication of how much we have.
This is, what's mind-blowing? If you ever try to transfer 50 gigabytes or 100 gigabytes of data from A to B over the internet, how long that takes. Now, you're telling me that you have a terabyte of data per day transferred over, I don't know how many.
Many.
and like the distance to Lagrange 2, what's the distance?
I don't know actually, it's very far away, definitely extremely far away.
Now just imagine every single day. This is a miracle.
Yeah, actually. So this is where I'm saying, like the technological development that it was necessary to make the science case of Euclid happen is extraordinary. Our instruments on board, they were designed particularly to trace these hints, these subtle hints of the accelerated expansion of the universe and therefore dark energy. Like putting it on space and to make able to come up with a telescope that it will support these two instruments, was already a challenge. Like being able to operate for the duration of what the mission required to take pictures of 1/3 of the sky, like technology in terms of telecommunications that actually, I might say, and I'll be a little bit patriotic here, but actually this is the contributions of Spain towards the mission. So CENER, one of our Spanish industries, were the one responsible for the K-band antenna. Yes, it's simply admirable. And I think that is really important as well to understand the times in space research, and especially in cosmology, because when Euclid, how the European Space Agency operates, it asks the scientific community, please tell us, what would you like to be dedicating your scientific efforts on? And it basically requests for proposals from the community.
Well, I guess your inbox got swamped, like ESA's inbox got swamped.
Yeah, so Euclid was the merge actually of two different proposals that came from two different scientific communities that they were proposing to do similar science, but one taking pictures and the other measuring distances to galaxies. So the European Space Agency saw a possibility here to actually combining both instruments, putting them in a spacecraft, and this is how Euclid was born. When these missions were proposed, these two proposals reached ESA was around 2007. Euclid was adopted as a medium-class mission of the European Space Agency Cosmic Vision Program in 2011. We launched in 2023. And the first cosmological results, hopefully, if we are up for the challenge, that I think we are, they will see light of 2026. So 20 years after, my colleagues in the community thought, okay, this is possible to be happening from space. So
I'm wondering, you have access to the secret vaults of the Euclid mission. What is known already from its findings, from Euclid's observations about the big question?
I wish that I could actually tell you. Right now, we are still in a process of further understanding our instruments to verifying that everything, I wouldn't say works correctly, but that we are pretty much in synchrony in the understanding of the instruments, but also how all the data is being processed. Because at the end of the day, it's about the big discoveries, but you want to be sure that if there is a big discovery out there, there is no question whatsoever that this could come from the fact that we did not understand really well what it was happening with the raw data. And we already have some cases in the past where it was believed that a very important discovery happened. And at the end of the day, it was pretty much like a poor understanding on different, what we call systematic effects. So really not understanding how our instruments themselves are behaving, so we cannot correct for all the different uncertainties associated to them. So this is exactly what we are doing right now in Euclid. So the Euclid mission is led by ESA in operations, the scientific exploitation, and the instruments are responsibility of the Euclid Consortium, the scientific collaboration behind. So thousands of scientists working extremely hard to make the Euclid science happen. And right now we are very busy processing the first 500 square degrees of observations of Euclid. That will give us an indication of, that will give us the opportunity of testing our data processing pipelines and further understanding of our own universe so that we can develop robust, in this case, scientific intuition rooted in really seeing results of how we are doing things for, okay, now once that we go to these 2,000 square degrees, that it is going to be the first cosmological release that is already double, it will be competitive to what it has already been happening from the ground-based telescopes. If there is some hints that finally we are breaking with this standard cosmological model, that I'm really looking forward to the case to be like that. So we need to be sure that there is no question whatsoever that, okay, there is something that we missed in terms of understanding of our instruments. So this is exactly what we are doing right now. This is where we are putting like all our energy. So understanding the instruments and how to model all the different statistical uncertainties associated to the systematic effects, so that once that we process these 2,000 square degrees, if there is some hint that there is something in there, we are pretty confident to tell to the community, hey, this is what we found.
Mm-hmm. If we assume, or if we see the transition from Newton, from the understanding of Newton's findings to Einstein as a paradigm shift, do you see another paradigm shift coming necessary in order to get an understanding for the original questions that we were discussing? Or could it be that we are making a mistake at the moment because we're looking at something the wrong way?
I think that it will be somewhere in between, because I do not like to portray this. I don't think that it is fair to portray this transition between Newtonian gravity and Einstein theory of general relativity as two completely different. It was revolutionary, but it was revolutionary in the sense that the theory of general relativity was opening up different scales and new possibilities that Newtonian gravity could not.
So it's an augmentation.
Exactly. But one of the exercises that I always ask my students to do is that try, in the limits that we know of our Earth, like distances to Earth, Moon, so on and so forth, recover Newtonian gravity from the theory of Einstein. And this is something that you could do. So it was like, okay, so suddenly with Newton gravity, with the work of Newton, so we have access to basically describe how gravity works in our scales of Earth, pretty much, or like the moon with some planets, so on. When you already go to very far away planets, and especially in communications, you need to include corrections from the theory of Albert Einstein. But then we have like this revolutionary approach of understanding how gravity actually works from Albert Einstein, and suddenly you have access to longer distance to study really in detail and really robustly how the laws of gravity work. I think that now with Euclid, or these approaches that we are doing in modern cosmology, we will open it up like a new door of understanding how gravity works on a even larger scales.
But that doesn't mean that relativity is wrong.
No.
It's just a new and open door.
Exactly. Yeah. So I think that it's just that it would be like, at the end, a theory is a mathematical model that we have to describe how nature works. And it's always per se incomplete. We do not have a theory of everything. Even on different subfields of physics, we have like different models that work particularly for sub-problems of physics. And in this case, what we are studying is gravity, really understanding how gravity works in space, in the universe. So I think that we will see something more on towards this line. So potentially like open up a new door of this model just to give us like more possibilities in terms of further understanding. But we are not saying, hey, Newton was wrong or Albert Einstein was wrong. And I think I'm really trying to put my best in terms of outreach and communications to focused on these details, because we already messed up with the term dark energy in terms of like, okay, it's not really dark. So this is where I'm saying we are not going to break with the theory of general relativity of Albert Einstein. There is possibilities, and it is likely that we will say it is incomplete, of our understanding of that theory was incomplete. And I think that this is most likely what it will happen.
That's why they say standing on the shoulders of giants. The giants don't go away.
Exactly.
They don't go away. We just keep building upon shoulders. I think that's a beautiful analogy.
Yeah, exactly. Yeah. Indeed. This is what most likely will end up happening by the end of, or hopefully this was what we desired, that after the Euclid final operations, and we have like this beautiful 3D map of the universe on 1/3 of the sky, we could potentially work towards that direction, that we will have like a new theory that will still be based on what we knew before, but it will open up the possibility to think further.
From the very beginning of Euclid, you mentioned 20 years ago, I think a lot must have happened in the meantime in theory also amongst theoretical physicists, cosmologists. So if funding were not an option, a question and a challenge, would we now build a telescope that could do profound new observations that we would never be able to do with Euclid and with all the new telescopes? Would we do something profoundly different or just augmenting on what we're having at the moment if funding is not an issue? Because I'm just asking, is there a promising theory you would love to observe at the moment?
This is a very, very good question. And a question that I'm starting to carefully think about now that I've been studying cosmology and I've been a cosmologist. I would say cosmology has been on my life for 10 years now, so over a decade. A decade is still half of the time that it has taken for Euclid between its conception, adoption, and start collecting the first data. The first contact that I had with cosmology precisely was doing very similar stuff as we are doing with Euclid. Instead of from space, using a beautiful telescope, Japanese-led in Hawaii, that it is called Subaru. So with Subaru, and this is one of the things that I do in every outreach talk that I have opportunity to, because we already have like some overlap with the observations of Euclid with Subarus. So I take like an image of Subaru and then I overpose it with Euclid so you get like the sharpness of why we're going to space. But if you think about it in terms of like the real mechanism that we are using, this approach of assuming that the apparent shape of galaxies gets distorted because there is matter in between those galaxies and us, so this gravitational lensing, that it is one of the mechanisms that Euclid have to basically trace where matter is in the universe to create this map. That is one of the outcomes of the theory of general relativity. And it is the mechanism that we are pretty much using these days for Euclid too. And when I started working on this 10 years ago, it was on the flourishing of demonstrating that potentially this could happen. Mm-hmm. And now that we are certain that it works, we are going to space. Mm-hmm. So with this, what I want to put as a manifest is that even the theory continues evolving. The history of science or history of physics tell us that these revolutionary concepts happened on a really drop and scatter way. And that science moved forward by rooting on these extraordinary, amazing ideas, but making them go from is a concept to, okay, let's use it. And from being a concept and let's use it, requires like a lot of work, infrastructure work, like development work, and also theory work. So what have happened between Euclid being adopted and Euclid now is that we have refined pretty much our equations. And actually, this is the work that I do for the Euclid Consortium. So one of the roles that I had within the Euclid Consortium was revisiting how we basically agreed on having what we call scientific requirements. So how well we have to measure the shapes of galaxies to be able to detect the subtle traces of dark energy. And this was done with the knowledge that we had in 2007. And part of my work has been, okay, so let's revisit how far away are we from the numbers that we provided like 20 years ago. And one of the outcomes is that, okay, we have refined our scientific requirements, but they are not that far away from what we thought that it could potentially be the case 20 years later. And that already gives us like a really important indication that, okay, so what we are doing is, I wouldn't like to say fine tuning, but like really, like making the equations way more precise and our understanding on the instrument so precise, our modeling so precise, so we can really discern between models. What the future has to hold, given what the landscape is looking like these days, I think that the future of cosmology will be in what we call like multi-messenger cosmology. So right now we are looking at our universe pretty much on the light spectrum. So we're talking about the visible, our near infrared, but we've never have observed the universe as a whole in the eyes of gravitational waves. So gravitational waves are a prediction of the theory of general relativity as well, that tell us that objects that have mass in the universe and are really massive and they move and they interact through gravity, they also emit some kind of waves really similar to the waves associated to photons in the light spectrum. So it offers us like a new way of seeing the universe with different eyes, with a different set of glasses. Right now, we had the first discovery of the first gravitational wave event. It was already back in 2015, 2016. That was one event. Now we have like hundreds of events. Like the future, we already have experiments that they are building up, that they are approved for going and studying the universe using gravitational waves, either from the ground or from space. And I think that cosmology will go towards doing this multi-messenger. So we look at some part of the universe, both in gravitational waves and both in the light, spectrum.
But this could already be done, right?
It could already be done.
I mean, like if the community agreed on an event,
oh, yes.
and then synchronized all their telescopes and everything they had on that event.
Yeah, look, I'm going to tell to the public a little bit and to the audience, like one of the most amazing anecdotes that I have of my short career. Indeed, like this has already happened. We already have observations, and this is why we know that it works. We already have observations of some events that could be seen both in light, so in the normal light spectrum, and in gravitational waves. Now, we know that it has to be objects that are really massive. So the gravitational waves signature is strong enough so we can detect it. And you know that it have to be objects that are also seen in the visible range, like in light. So it's not about finding two supermassive black holes that suddenly they're merging with each other, because you wouldn't get to see that with your telescope. We had to wait until the mergers of really heavy compact stars, and those are neutron stars. So once that we had the first detection on both gravitational waves and light of two neutron stars merging with each other, we rule out so many different modified and dark energy theories, because some of these theories already predicted that the speed associated to the mathematical concept of the field behind dark energy must show differences between the propagation of gravitational waves and the propagation of light. So most of these theories predicts that actually gravitational waves also have a speed as the speed of light, so the same value, but some other did not. And with this particular measurement, it was demonstrated that the light of the speed of gravitational waves is pretty much the speed of light. So they were already like many, and now the anecdote is that basically LIGO was the one that was basically behind the observation of gravitational wave, put back in a social media many years ago. Tomorrow we are going to be doing an amazing discovery. We're making an announcement of an amazing discovery. The community was already expecting, because as you said, this could be done now. So the people were already expecting that eventually this will be something that it will happen. And theoreticians, cosmologists in theory, wrote papers, like papers assuming that the speed of gravitational waves was equal to the speed of light, papers that thought that, okay, this is not the speed of light, and they were just simply waiting. So a few hours after the discovery itself and the announcement, we already have like published articles, just because we have like some millennial scientists on social media that they already have gone through all our theories and say like, yes, no, yes, no, yes, no. And this already tells you when there is something exciting and something that it has like sufficiently hype, science moves extremely fast. Yeah. Now, what do we actually need to do cosmology for multi-proof events? We need many. In exactly the same way that we are going to space to measure like millions, to classify and to survey like billions of galaxies, we will need to do something similar for gravitational wave events. And we are not there yet. So we are talking about like 100. We are seeing in gravitational waves as it happened with galaxy surveys 20 years behind us. So I think that we still need to wait, but definitely tons of work to do in this direction to start modeling how to do multi-proof cosmology.
Artificial intelligence is everywhere.
Oh, yes.
Is this also something that is of interest to cosmologists?
Yeah, these days, given how complicated our modeling is becoming, because as I said, we really need to understand well of our instruments. You really need to understand extremely in detail all the systematics, so all these effects that you really need to take into account. Otherwise, you can get dark energy signatures mistaken by something else. You need to rely on artificial intelligence to be able to do the computations. So people believe that artificial intelligence will one day come and potentially say, instead of like, okay, Dr. Guadalupe Cañas Herrera, I will be relevant in terms of answering the question, what is the best cosmological model that fit the observations? I think that, artificial intelligence will definitely not be there anytime soon. And definitely not in the time scale of answering the question, what is the nature of dark energy? But it offers a really powerful tool to give us scientists and cosmologists the opportunity to perform computations that otherwise would be impossible. Something really straightforward. We're taking pictures of the deep space. We have galaxies, we have stars, we have other objects. We don't have enough human eyes to classify. Exactly, to classify. And I use artificial intelligence and machine learning in my work to be able to perform the statistical analysis that we need to carry out to compare these really complicated and complex models of the predictions of our universe with Euclid data, really at the level of purely fitting data. So having some points with some error bars and trying to find the best fit all over the data, the best theoretical line that will fit all that data. I need to rely these days on artificial intelligence. Otherwise, these computations will take months to be accomplished.
This is the obvious assistance of AI. But what I would like to find out is as to if it can also conceptually support. Because to me, AI, I'm in the creative industry, so my job is to be creative and come up with new ideas. So AI has never really impressed me with novel ideas I would never think of, but it would give me hints to think in certain directions. So when for example, I would prompt an AI, give me 5 suggestions for this and that, it will give me 5 suggestions and I will go like, oh, 3 is interesting. And this inspires me to think in a certain direction.
Yeah.
Could this be something of interest in your world?
Yeah, well, this is already happening in the sense that we scientists are pretty much detectives of what the data can potentially tell us. The more data you can process, the more patterns you can find on the data, the more you can think forward in terms of, okay, what's next? And this is something where we get the help of machine learning and artificial intelligence to be able to give us indications of something that is not going well or it's not going the way that we thought. For instance, Euclid is operating from space. We have the sun behind us, but relatively the sun is close to the spacecraft. We know that the sun is producing like really high energy particles, and our detectors, our cameras actually trace some of these particles, what we call cosmic rays. And like what you see in the images are like really thin, the straight rays that they are covering. We really try to filter that with machine learning. But something that we have discovered really recently, also with this happening in other surveys or in other experiments, is that once that we start processing further the data, we had classified like really short cosmic rays as really elongated and really lensed galaxies. And you only get to see that when you have relying on machine learning, when you tell them like, okay, from all the millions of shapes of galaxies, what you have classified as galaxies, tell us if basically those shapes kind of make sense. And then you get to see, okay, no, they are like a population of objects that they are too elongated, that they are really looking weird. And it already gives you thinking, okay, no. So most likely my filtering of the cosmic rays and the filtering of the raw data is not taking place the way that it should. This is a really stupid example. But at the end of the day, we are repeating and repeating this almost in every single process. And without machine learning, we will not have the possibility to encounter like some of these many things that potentially can go wrong in the processes, in the processing pipeline, in the analysis of the data. Now, in terms more from the theory side, what we're using artificial intelligence mostly is in speeding up, boosting, and answering the question of, okay, I have this alternative theory. It is really worth going through all the pain and the sweat and the work that it requires to compare it against the data? Or can we use some signatures or some patterns that are easier to be identified that will allow us to say, before going into getting our hands dirty, hey, is this model worth? Exactly. Does it make sense? So this is a really promising work in the field that it is called machine learning model selection. I'm actually working on that actively. So just to give us some hint and to ease our work further, if I have like a pile of 100 theories that I would like to test against Euclid data, resources are pretty limited at the end of the day in terms of computation, humans, so on and so forth. So you really want to see which ones you put in the pile of, okay, let's make it happen.
Do you have your own LLMs, or do you work with the public ones?
I usually work with public ones or with some within the Euclid consortium and in general within the scientific community. We based our work in open science, and most of us are really strong defenders of open science. So if you develop something, you put it on the community, you always cite back just to give the acknowledgement that it is pretty much necessary, but also appreciated from the community. So we are all benefit from growing up and making things more stable or making things like suitable for all the different problems. So at the end of the day, you ended up having like some hybrid algorithms that they are based on some public libraries from general machine learning providers, if you want to call them like that, but that you modified, but then maybe some other people will modify further. And I think this is one of the most beautiful things that we are seeing now with, not only with modern cosmology, but with astronomy and with physics, that we are pretty much getting oil engined in the open science approach with fair principles, which is something that I really, really, really like, and I feel deeply connected to.
I'm still awed by the notion you made about looking 10 billion years into deep space. What is out there? What do you think is behind there? Does this place at a distance of 10 billion light years look like the place, like our galaxy? Is space a homogeneous place?
So this is indeed very interesting question. This is actually one question that we are trying to answer within Euclid. So you don't send, as I said before, like a really expensive spacecraft to space without having a really solid scientific case. And now I'm going to extend that statement. You don't send such a expensive spacecraft having only one single scientific user case. There is tons of things that you can do with Euclid data, like in so many different aspects. Like, of course, the ultimate goal, understanding the nature of dark energy, saying something about dark matter. But with the data that you have that provides like really fast statistics, because you have like so much data, you can answer these questions. Like, for instance, is the universe isotropic? Is the universe homogeneous? Has the homogeneity of the universe changed over cosmic time? So within the Euclid consortium, apart from being a very dedicated scientist, I'm also a very dedicated scientist right now with coordination responsibilities. So I'm the coordinator for model extensions beyond the standard cosmological model for the first Euclid cosmological data release. And this is one of the questions that we have very brave scientist willing to answer behind, which is really saying something about the homogeneity of our universe. How does our universe look like between now and few billion light years behind us or in the past? So that would be between redshift, as I was saying before, redshift 0 and redshift 2. Pretty much it looks very similar. Like, if I will give you in terms of like images, it's not that suddenly you're going to see fewer galaxies, or you're going to see like galaxies that not anymore are spiral galaxies and they tend to be irregular because the gravity didn't have the time to make them rotate without momentum and start forming the arms. They will be really, really similar. And this is the challenge. We know that something is happening between that time and us, which is that our expansion of the universe started to accelerate. But you wouldn't see it. You will only see this effect when you studied millions, billions of these galaxies statistically. So you think about it, is doing statistics with so much data, because otherwise it will still be invisible to us. It's not like, for instance, going to redshift 10, so really what we call close to the dark years, where the first stars and the first galaxies are starting to be formed. With Euclid, we are building this wide catalog, which is the catalog of 1/3 of the sky. We would like to, and we are planning, and actually this quick data release that we are having next week is going a little bit deeper. So Euclid, of course, if you let it be and let it absorb more photons, it had the possibility to go deeper in magnitude. So that means accessing objects that are even farther away, but we will never have the capacity to discern or to discover something as, oh, wow, let's see how our universe was looking like when the first stars were formed. Euclid is an exercise of really big data and doing statistics with really large data sets. And only by understanding this large data set and the statistics behind it is when we get to access to answer those questions. Really important in cosmology.
Fantastic. The obvious question that needs to be asked, do you think we're alone?
Oh, yes. That question. Not oh, yes, about like whether we are alone, but yes, indeed, like one of the questions that I always get asked. Definitely not. We are not alone. Like,
definitely not. I like that one. That was very...
definitely not. I don't think... Look, I think that there are many different aspects that as mankind make us unique. And I think that everything up to some sense is unique on its own. But we can't be. What it makes us... think and what it makes us potentially access to answer these questions that we have about the universe, that chemistry behind, that biology behind, cannot be unique. In the sense of we are in a pretty much average planet, using pretty much average ordinary matter, in a very beautiful solar system neighborhood, but at the end of the day with a pretty much average star, in a pretty much average spiral galaxy, which is our Milky Way. Like, I'm seeing the spiral galaxies in Euclid every single day, like hundreds of them. Pretty much average, all of them. In a pretty much average area of our universe, which is our local group. In a pretty much average universe, because it's not that our universe is really intriguing and there are many things that we don't understand, but it's pretty much a standard. It's not that we need to rely on coming up with new, dark energy definitely is something that we need to understand, and it is 70%, but we could also potentially explain that by revisiting our laws of gravity. It's so highly unlikely. At the end of the day, my job consists on doing statistics. I do statistics with cosmology. I'm a cosmologist. I'm not going to say that I'm a statistician. Otherwise, my husband, the statistician, will kill me. But in any case, it's so unlikely that we are alone. I think that the question that is worth answering or thinking about answering or start even asking more is, will we ever have the possibility to contact other, I'm not going to say people, aliens, or we will have the possibility to see or to get in contact with other forms of life in the universe? I think that is the question that really we should start putting more focused on our head.
I think I'd rather we're alone, because it's too frustrating to know someone is out there I will be never able to visit. That's profoundly frustrating. So I'd rather be alone.
You'd rather be alone. Maybe I have already come up with my terms that actually we are not alone. But in exactly the same way that I know that I will not visit all the countries of this fantastic planet Earth, it doesn't mean that I will have the possibility to meet everyone out there within the universe. Hopefully, maybe that will be more into the terms of sci-fi, but what we thought that it was sci-fi like 700 years ago wasn't anymore now, right? Who knows? Maybe in the very long-term future, we will have access to some other kind of communications that will allow us to answer like that question. That, okay, so can we get in contact with other forms of life out there? But but definitely no. Yes. I don't think that we are alone. No.
Guadalupe, would you be ready to go into space if the call came, if someone asked you?
Oh, I must admit that I don't think so. And the reason is that I think that I will go because at the end of the day, I'm driven by challenges. I'm driven by discovery, and I have this innate curiosity that really makes me thrive in so many different aspects of cosmology. I started as a theoretical cosmologist. Now I'm going more in towards observation, and I have questions about so many different things. So I think that ultimately I would say, okay, if this is just one life chance, I'll just take it. Myself pursuing actively a career as an astronaut, no. I am feeling like really comfortable in this planet Earth. I think that I can make some impact in my planet comfort zone. I must admit that I'm extraordinarily afraid of flying, even though that doesn't stop me to perform like collaboratively science all over the world. But yeah, like I think that I will do it because I would not like to be at the end of my life thinking, what? You did not do it because of fear? Like, no, definitely not. I will do it. But I believe that there are many things that we can still do from here, like that requires our work and dedication. Yeah. And this is where I'm definitely willing to continue pursuing and working hard.
Provided you had to go by force, traveling in space is exciting, but can quickly become boring because of the vast distances. So we thought we set up a playlist on Spotify and asked each guest of the Space Cafe podcast to contribute one tune, one piece of music they would not want to miss on that very boring journey. Which piece of music would you want to put on that playlist?
This is any kind of question, any kind of song. Oh my God, I really love this question. It's amazing. I think something that sets me apart as a theoretical cosmologist is that I'm very friendly and really talkative, and I really like to bring people together. And I think that this is one of the reasons why, like, beyond being a scientist, I'm also an sport instructor. So I'm a Zumba instructor, which means that I have music pretty much all my week alone in my classes. I definitely think that I will choose something like powerful, maybe with merengue rhythm, like something fast, something that I will hear at least once per day, a short, 2.5 minutes song that will basically, energize me. that it has to be a stupid. It could not be a song that has like deep lyrics that will make me think or will make me feel nostalgic. I think that it has to be something like really catchy with probably like in something.
Like what?
Like what? I think, I don't know, maybe some, so something like Suavemente Bésame, merengue. Like it's a very catchy song, and it gets repeated like in groups of 8. So it's really easy to get within the song. Or maybe something more actual. Like there is a really powerful Zumba song that it is called Tiki Taka. That is really, really stupid. So it would be like something, again, really short, 2 minutes and 30 seconds, but it has like a lot of energy. Something like that. Cool. Definitely a merengue.
Fantastic. One last question. This is the Space Cafe podcast. Now and then you go to coffee places to energize yourself with coffee. I challenge you to share a shot of inspiration, an espresso for the mind with me, with the audience. What could be a shot of inspiration you'd like to share? Any idea, any topic you think could be inspiring?
Well, I think that I would take this opportunity. My espresso will go to the next generation of cosmologists. I'm starting to develop my career as an independent scientist and to start asking myself like questions about the universe that might potentially look like crazy, but I'm now able to put like some scientific wisdom of knowledge behind it. So I would just advise, if you have like any kind of curiosity on you, do something. And even if it is just on your smartphone, or even better, like, cause you will get attached to that memory, have just a small notebook. And if there is some idea, random idea that you have during the day, just write it down. Like write it down. And just make me a favor, like 10, 15 days after, just have a look at the list. Just have a look at what has been populating that list on your smartphone or in this small notebook that you might have. And then ask yourself again, would you repeat that question if circumstances will change? Sometimes you get inspiration just because you're chatting with friends, because there is something that you saw that makes you connect with something. Now, I want you to repeat the same question, but based on the environment that you have around you, and think if you could like give it a twist of what it meant. And you will be surprised that this will help you thinking out of the box a lot. And for me, it has been definitely something that made me come up with really interesting ideas that I thought that they were crazy, and not necessarily. And they ranged from not only physics, cosmology, but even how to do better in my Zumba classes, like get more students into movement. So yeah, just start thinking about that, even, but just with your morning coffee, like every morning, like just write down whatever crazy idea you might have over the day, and then thinking again, like in a few days after.
Guadalupe, thank you so much for taking the time.
Yeah, thank you so much for the invitation. It's been a pleasure.
And that is a wrap, my friends, for a literally stellar episode. I loved the notion when she said that it's one of the greatest tragedies in space marketing ever to have labeled dark matter, because it's just not. It's just, well, we've talked about it quite at length. So why don't you, like right after this, sit down, grab a pen, something to write, like a piece of paper, and write down your craziest ideas you've ever thought of, and then revisit them in a week from now. I think it's a fantastic experiment you could do, thanks to the shot of inspiration that Guadalupe just shared with us. Thank you, Guadalupe, for poking our brains, for inspiring our minds. If you, my friends, like what we do here, consider sharing this episode with someone you like, with someone you feel like you would like to surprise, you would like to rekindle a conversation or strike up a conversation, perhaps with the stranger. And how cool can it get to talk about topics like this? Anyways, there is something new. You can leave us a voice note if you want. Let me check. What was it again? It's no. I'll add it. I'm so sorry for that. I'll add that to the show notes. It's a URL where you can very easily drop us a voice note and perhaps be featured in our next episode. So if you have always wanted to share a suggestion for a guest you'd like to hear, what you'd like to see, or just let us know how we could improve our show, this is one of the places. And of course, there is Substack. So why don't you head over to Substack? It's a fantastic place if you really want to read in-depth information. Still pretty much void of any social media blurbs and what is it called? Stupidities. Time-consuming black holes. I think that's what I was what I was trying to refer to. Yeah, Substack is a pretty cool place. So why don't you check out not Human Chaos. It's the Space Cafe podcast on Substack. Well, yeah, leave us a rating or two or a review on your favorite podcast platforms. And other than that, I'm really looking forward to hopefully surprising you in 2 weeks from now. Until then, bye-bye. Take good care.